We're going to dip a little bit deeper into the geometry today. Today we're going to work with triangles. There's a few things that we're going to take care of. Some very preliminary stuff that we'll breeze through here. We're going to see that there are actually two methods for finding the area of a triangle. Everybody knows one method, the formula for area of a triangle, but there's a second method that's very old and not well known that we'll explore. We're going to use the Pythagorean Theorem to find the missing side of a right triangle. Quick refresher on Pythagorean Theorem because there's a fair assumption that you're at least somewhat familiar with that. And then we're going to spend most of our time today on particular special triangles and similarity. There's a couple of triangles that are particularly useful in geometric problems. We're going to spend most of our time working with those. But first of all, let's start out with just triangles. First of all, the formula that you surely remember from at some point in your life, area of a triangle. We know that if you've got a triangle, we can identify a base and a height, or the height is often called the altitude. And if you know the base and the height, you can find the area of the triangle by taking half the base times the height. That should not be news. But there is one criteria that the height and base have to meet. And that is that they must be perpendicular. Does the altitude of the triangle necessarily have to be inside the triangle? Doesn't necessarily. It just has to be the distance from the top down to the bottom in a perpendicular direction. So we'll just look at a quick example here. We want to find the area of that triangle. Now we know a few things about this triangle, and we have a bunch of additional information there that we certainly do not need. Okay, well, we want to find the area. First, you need to identify your base and your height. What are the two dimensions up here that are useless to you? That 13.385 is certainly no good, and the 7.56. Neither of those are a base, nor are they an altitude. Now, we could treat that 13.85 or 13.385 as the base if we knew what this distance was. Then that would be our altitude, but that's not the case. Here's our altitude or height. There's our base. Very basic algebra says that the area is going to be 1/2 of 8.75 inches times 7.100 inches. And that gives us an area of 31.06. We can keep 4 sig digs, so that's what we'll do. We have 5, 4, and 4, and on our dimensions we'll keep 4 sig digs. 31.06. And those are square inches. We're done. And there's another formula for finding area, and it's called Herons Formula. Herons Formula will tell you the area of a triangle if, forget base and height, if you know what all three sides are. Now, the first thing that you need to do when using Herons Formula is you need to find out what the perimeter of the triangle is. Take the perimeter, divide it by 2. That gives you the S constant. And the S constant is used in the formula for area. There are a number of formulas that you'll need to memorize over the course of this next unit for geometry, and this is one of them. Also, the one previous to this was the formula for area of a triangle. So if you want to make a little star by that in your notes or something, these are formulas that you'll need to know. We'll do the exact same triangle and see if we get the same thing. Now this time, we're going to use Herons Formula, which depends on the three sides, which means now we're going to find the same area, but the dimension that's useless is 7.1. That's not one of the side lengths, and so that's of no use to us. So let's go ahead and find, the first thing we need to do is find the value of S, the constant S used in Herons Formula. That's half your perimeter. Your perimeter is going to be equal to 13.385. That's the distance around a shape. Remember, perimeter is the total distance around the outer edge. 7.560. and 8.750. Add those up, we've got our perimeter. That works out to be about 29.695. Which means our value of S is half that. And if we take that and divide it by 2, we get, and we're going to leave plenty of sig digs here. We'll just leave extras and round off at the end, 14.8475. Okay, now we can proceed and use the formula for area, now that we know what our S value is. Herons Formula said that the area is the square root of S times S minus one of the sides, A, we'll call it, times S minus the second side, B, times S minus the third side, C. So if we fill in our values, that's going to become the square root of 14.8475 14.8475 minus 14.8475 minus 13.385. Do all those values, find all the differences, multiply them out, take the square root. And if you do all that, take your difference here, your difference there, multiply them by 14.8475, take the square root, you're going to get an area of, anybody care to guess?
40.
Nice try. It better be the same area we had in the last example, even though we're using it a different way. It turns out to be 31.06. And your units again are square inches. Look at how those units come from Herons Formula, though. Each one of these differences would have units of inches. So you'd have inches times inches times inches times inches. You'd have inches to the fourth power. But then when you take the square root, you end up with inches squared. Okay? So we're left with inches squared, 31.06 square inches, and we're done. We found the area. Gabe?
That ultimately won't matter.
Okay. Now, think about this. Is there ever any danger that one of these parentheses, one of these subtraction values could turn out to be negative? There's no way. Because S has always got to be bigger than these three sides, right? This is half the perimeter. That has to be bigger than all three sides. So these will always be positive. It's no danger. The other famous fact in regards to triangles, of course, Peregrine Theorem. That's right. Herons Formula works for any triangle, regardless of angle measure. But the Peregrine Theorem only applies to right triangles. Now, a little terminology here, as shown up on the screen. But when you're dealing with a right triangle, you do have specific names for sides. The two sides that form your right angle are called the legs. They, of course, are always assigned the values A and B. The third side, which is C, is hypotenuse, which, if you're ever playing Scrabble, is worth a lot of points if you can get the U on the triple letter score. Thanks for asking. A squared plus B squared is always equal to C squared if these two are the legs of a right triangle. And of course, since that's always true, as long as we know any two sides, we can find the third one, whether the unknown one is a a leg or a side. So let's work one example with the Pythagorean theorem, then we'll move on past this. We want to determine how much stock you need to make this bracket that's shown. Get you a little better picture of that here. Well, believe it or not, it seems simple, but probably 3/4 of the mistakes that I see involving the Pythagorean theorem are from assigning the side or the letter values to the sides wrong. Taking care with that, C has got to be the hypotenuse. A in this case is going to be 16 inches and B is going to be 12 inches. We'll leave this 3-inch tail and add that on at the end. We're really just concerned with this triangle, which is a right triangle. So we know that our 16-inch side squared plus the 12-inch side squared is equal to the hypotenuse squared. 16 squared is 256. Twelve inches squared is 144. So C squared has got to be 400, which means C is equal to the square root. We don't obviously need to worry about plus or minus square root here because that's a distance. It's got to be positive. Square root of 400, and so C is 20. Paying attention to significant digits, we had 4 there, 4 there. We might as well keep 4 on our value of C. And then finally, to answer the question, how much stock do you need? Well, we can just now add up all the pieces. The length is going to have to be 16 plus 12 plus 3 plus 20. And let's see, what does that give you? 36, 48, 50, 51 inches. And we're done. Okay, what we're going to do for the rest of the time, we'll work with special triangles and similarity. This is a pretty fundamental fact from geometry in general. We're not going to do any examples directly related to this fact. We're going to use it a little bit later on. But in general, if you have two triangles that are similar, that is to say they have the same shape but different size, they could be the same size, but generally they don't, then all their angle measures have to be equal. And corresponding sides are going to have to be proportional. So for example, A prime, the A side of the smaller one divided by A, that's going to give you the same ratio as B prime divided by B or C prime divided by C. We'll come back and use that fact in just a minute, but the reason that we make a note of this now is because there's certain special triangles that are of particular use. First of all, there's one particular triangle called the 45-45-90 triangle that you want to get to know well. Take any triangle that has a right angle and a 45-degree angle. By subtraction, and what we established yesterday, what does the other side have to be? It's got to be 45, which means what has to be true about the two legs on that right triangle? Now, I've got them drawn as 1, 1, and square root of 2 up there, but that doesn't have to be true for every 45-45-90 triangle. They got to be the same length. Why? If you turn this thing over and look at it like this, if these two angles are the same, we have a symmetric triangle, so those two sides have to be the same. So it's a pretty fundamental fact, but we can't take it for granted. So those two lengths are going to be the same. Now, that means that if you know one leg on a 45-45-90 triangle, you automatically know the second leg. And if you know both of the legs, you can use the Pythagorean theorem to find the hypotenuse. So for a 45, 45, 90 triangle, you can find all the side lengths as long as you know just one of them. Now here's a technique for doing that that works pretty slick. Assume that you have a 45, 45, 90 triangle where one leg has a side length of 1. Then by symmetry, the other one also has to be 1. Up there it shows it on the screen, but the reason that hypotenuse has to be the square root of 2 is by the Pythagorean theorem. A squared, which is 1 squared, plus b squared, which is 1 squared, has to equal c squared. So 1 squared plus 1 squared is 2. And c has got to be the square root of 2. That means that in any 45, 45, 90 triangle, the hypotenuse is always the square root of 2 times whatever the length of the leg is. Now we can use this proportion to find the missing values in any 45, 45, 90 triangle. Along with some of the geometry fact, this is another triangle or proportional fact that you just have to know. Okay, we'll be using it periodically. You'll be using it a lot in about 3 weeks. This seemingly simple fact is going to have very big implications when we go to memorizing trig ratios, which we're going to do. If you know this, memorizing certain trig ratios will be much easier. So remember those proportions now, and we're going to see them again in a few weeks. Now let's do a problem related to this. Let's find the perimeter of this triangle. Okay. Well, it's not even worth noting, other than the fact that it's worth noting. But what does this angle have to be? 45 degrees. We don't need to make a special point of that fact. It's just worth recognizing. Okay, so that angle's 45 degrees. Let's find out what the two legs have to be. Now, there's several approaches for finding the length of this leg. What's one thing that you could do to find the length of this leg? That would work, and I think the principle that you're using here is that you're using the Pythagorean theorem to do that, because we know that a squared, this side would be a, and if we take a and square it plus b squared, we would get this squared. A squared plus b squared equals 6.870 squared. That's certainly true, but what's true about a and b? They're equal. So instead of saying a squared plus b squared, we could say a squared plus a squared. Or in other words, 2a squared equals 6.870 squared. So 2a squared has to be 6.870 squared. Now we want to solve that for a. So what would we need to do? We'd need to divide both sides by 2, and we would get a squared equals 6.870 squared divided by 2. Therefore, a equals the square root of 6.870 squared divided by 2. Is that right? 6.870 squared divided by 2. So we can find it in that way. Take our side length, square it, divided by 2, and then take the square root. Yeah, good. Okay, so that's one technique. That's actually, there's an easier way. Divided by the square root of 2, because we know that this side is going to equal the square root of 2 times the length of this side. Or to say that another way, this is always similar to our little 45, 45, 90 triangle with sides 1, 1 and the square root of 2. And we have a similar triangle proportionality here. We've got 6.870 over the square root of 2. That has to equal b over 1. 6.870 over the square root of 2 equals b over 1. There's our proportionality. That's a similar triangle fact that we just used. Agree? Well, there it is. Solve for b. B is already solved. Over 1 doesn't really change anything. So b equals 6.870 divided by square root of 2. And you get, I forgot it already. I should have had it memorized. Thank you. 4.857 with 3 sig digs. 4.858 inches. Everybody agree on that side? Use whatever technique you want, but this method is a lot less work than going through the Peregrine Theorem. Which means A has got to be 4.858 inches. And our perimeter, which is the question that we really wanted to answer, .858 plus 4.858 plus 6.870, 16 point. 586. We're done. Okay. Good. Well, this special triangle's got a brother, the other special triangle we're interested in, the 30, 60, 90 triangle. Now this one's got a little bit more going on. Now we've got a 30, 60, 90 triangle. The sides are always going to have the same proportions. The question is, what are they? Now there's a couple of different ways that you can think about these proportions. Here's the method that I like. Let's establish one of these 3 sides. Now we could establish either one, but the easiest way to remember it is if we say that the hypotenuse here is equal to 2. Now, does anybody see why if the hypotenuse is 2, this side, the short leg, has got to be 1? Well, think of this as half of an equilateral triangle. Pretend that there's another half of a triangle down here that looks just like it. Now that angle is 60, this angle is 60. What's this angle? 60. And if you've got 3 60-degree angles, this is an equilateral triangle. All 3 sides are the same, which means this side has to be 2. But since it's only half there, it must be 1. Okay? Well, this side has got to be the square root of 3 by, no, not symmetry. Instead, the Pythagorean theorem. Let's call this side our unknown value b temporarily. 1 squared plus b squared equals 2 squared. So that means b squared equals 4 minus 1. B squared is 3, which means b is equal to the square root of 3. Those proportions are always going to be true. Now, one way to remember this is that the shortest leg is always half the hypotenuse, and the longer leg is always the square root of 3 times the shorter leg. So if we know this value, we can find the other two pretty quickly. Or you can always set up that triangle and set up a proportion, and that's how we'll handle it in the next example. Here again, that triangle is going to show up a little bit over the next couple days, but a lot in a few weeks when we work with trig ratios in the unit circle. We'll be turning it all around and treating it as the same triangle used several different ways. But let's do one example involving a 30, 60, 90 here. Let's find the area in square feet of that triangle. It's a 30, 60, 90, and the longer leg is 4 feet 8 inches. As long as we want the area in square feet, let's put all of our dimensions in purely in feet. 4 feet 8 inches is 4 point. Right. It's 4 2/3. 4 8/12, so that's 4.66 feet. 4.66666 or 4.667 feet. Okay, well, if we want to know the area, we need to know either both of the other two sides if we want to use Herons Formula, but that's an awful lot of work since it is a right triangle. Let's just do this the easy way and find the base. Okay, well, you have a couple of different methods for finding the short side. What's one thing that you could do real quickly? Nope. You could, this side is always the square root of 3 times this side. So you could reverse that and just take this number and divide by the square root of 3. Now again, that's a little tricky to remember. Instead, well, it can be. Instead, let's just set up a similar triangle to remember that. Here's our 30, 60, 90 triangle. Now the short side, in relation to the slide that we had, this short side is called 1. The hypotenuse is, and the long leg, square root of 3. So now set up your proportion. We know that 4.666 repeating, we'll just keep a few extra sig digs, over the square root of 3 has got to be equal to our unknown side b over 1. Well, there again, b is already basically solved. It's 4.667 over the square root of 3. And if you take 4.667 and divide it by the square root of 3, you get 2.694 feet. Everybody agree on that for our base length? Okay. All right, well then we can go ahead and find the area. We'll use the less exciting of the two formulas. Area is equal to 1/2 the base, which is 2.694. Times the height, which is, rounding it to 4 sig is 4.667 feet. And if you crunch that out, you get 6.29 feet squared.
How can you get the sig digs on the 4 foot 8 inches? How does that work?
Right. The question is, how do you handle sig digs when you got 4 feet 8 inches? That's kind of a slippery question to handle, but if you were to convert this purely, your precision is to the nearest inch, right? So 4 feet 8 inches is how many inches? 4 feet has plus 8 is 56 inches. So you could call this 56 inches, in which case there are 2 sig digs. So properly, we can only round that off at 2 significant digits. And so if we cut this all the way back to 2, our answer actually has to be 6.3 square feet. And we found the area. Incidentally, we could have called that side 56 inches, figured out how many inches this side was, found the area, and then converted it into square feet. We could do that too, but this saves us a conversion step. Well, the last thing I want you to do here before we leave this problem is, even though we didn't need it, go ahead and determine what the length of that side is, what the length of the hypotenuse is for that triangle. Now, there's at least 3 ways that you could go about that at this point. What's one way you could go about finding the length of that hypotenuse? Take b and double it. At this point, that's the easiest way, and you'd get 5.388. Okay, once you know b, you could just double it to find out what the hypotenuse is. Everybody agree with that? What's another method you could have used? Everybody do it a different way?
Peregrine Theorem.
You could use Pythagorean theorem. You know the 2 legs, you could find the hypotenuse. Absolutely. A little bit more work, but it did certainly shake out. And the third method that you could use? You could go back to your original proportion. If we didn't know this, we could say 4.667 over the square root of 3 is equal to c, if we didn't know this, c over 2, and solve that for c. And we would get the same value. So there's several different options for finding that missing side. Okay. Now, that's about all that we can do with triangles without dipping into the ratios aside, which puts us into trigonometry, and we don't have time to dip into that today. So that's where we're going to stop.